Hello everyone, and welcome back to Virtual Thermodynamics. Today, we're going to be looking at air standard Brayton cycles. Brayton cycles are an important power generation cycle in the US because they're used in natural gas power plants and in jet engines. First, we're going to talk a little bit more about sort of the power plant version, but later on in the course, we'll look at how Brayton jet engines work as well. When we think about how to do a Brayton cycle problem, it's a bit of a combination between a Rankine cycle problem and an Otto or diesel cycle problem. It's a little bit like a Rankine cycle because we have multiple different components in our cycle and we treat them as open systems. So we'll be using the open system version of the first law. But it's a little bit like an internal combustion engine problem because we're going to assume that the working fluid is air. So when we start to fix our states, we'll use some of the same methods that you'd see in an internal combustion engine problem. So when we characterize the Brayton cycle, it's a heat engine. So we're going to be talking about things like thermal efficiency, where we're looking at the net work or the energy benefit divided by the heat in, which is the energy cost. We might also characterize a Brayton cycle by its back work ratio, remembering that the power plant is the first consumer of the power plant. So as we're running our turbines, we use some of that power to run our pumps, or in this case, compressors. So if we compare Brayton cycles to Rankine cycles, back work ratios in Brayton cycles tend to be fairly high compared to Rankine cycles. But the thermal efficiencies can be even higher than what we see in Rankine cycles. Like a Rankine cycle, we'll do an open system version of the first law. On all of our components, we'll assume that they're steady state, that there's one inlet and one outlet, that we can neglect changes in kinetic and potential energy. And then for each component, we'll choose whether it's adiabatic or whether it's passive. Just like most questions in the Rankine cycle, we'll assume that there's no friction or heat losses in the lines. And when we do that, we get these equations, which are hopefully familiar from Rankine cycle, where if we're trying to find power, we get m dot times h in minus h out. We'll let the first law tell us whether these equations are positive or negative. And if we're transferring heat, we'll get m dot times h out minus h in. So up until this point, when we're getting our symbolic solutions, this looks like a Rankine cycle type problem. But it changes a little bit when we ask ourselves, what's the fluid? Because when we ask what's the fluid, we'll remember that the working fluid here is air. But before we do that, I just want to look a little bit at what the PV and TS diagrams for Brayton cycles looks like. For open system problems, I tend to look more at the TS diagram. It's nice because it shows me which processes are isentropic, or where the entropy is constant. So as I move from 1 to 2, I'm going through my compressor. I'm putting work into my working fluid to increase its pressure. Then I add heat from 2 to 3. That increases the temperature of my working fluid, so that at state 3, I have a high temperature, high pressure fluid, and I let that expand through a turbine so that I generate work. Now, when I get to state 4, I have my air and I need it to cool down. So it goes through some heat exchange process where the air is cooled. Now this heat exchanger may not exist in my cycle. It may be that coming out of the turbine, my air is exhausted to the atmosphere, and then going into my compressor, I'm just pulling cool air from the atmosphere. So in a sense, this heat exchanger that cools my working fluid down is just the atmosphere. So when I look at the PV diagrams, I notice that I'm making the assumption when I'm going through the heat exchangers that there are no friction losses, because those are horizontal lines on my PV diagram. And when I'm going through my turbines, at least if I'm assuming that this is an ideal system, I'm assuming that as I go from 1 to 2 and from 3 to 4, those are isentropic processes. But isentropic processes aren't real. So how do we go from isentropic processes to real processes? We have to use isentropic efficiencies. So if we can define isentropic efficiencies, it looks a little bit different for turbines and pumps. So pumps or compressors in this case, because we're talking about a gas. So in a pump, the real turbine generates less power than the ideal turbine. So we put the real turbine on top and the ideal turbine on the bottom. And the compressor, the ideal compressor, consumes less power than the real compressor. So the real compressor is on the bottom. You'll know if you make a mistake here, if you ever get an isentropic efficiency to be greater than 1, then something is wrong. So now we start to think about what the fluid is in this problem. And like in the internal combustion engine problems we've talked about, the working fluid here is air. So we're going to use something that looks like an air standard analysis, similar to what we did for internal combustion engines. So we're going to neglect the fact that there's actually combustion happening in our working fluid and it's changing chemically throughout our process. For internal combustion engines, we assumed that we always had a closed system, but we won't do that here because each component in our cycle is really an open system. In internal combustion engines, we also assumed that all processes were reversible, and we're not going to limit ourselves that way here with Brayton cycles. We can use reversible turbines and compressors, but we don't have to because we know about isentropic efficiency. We're still going to assume that the working fluid is an ideal gas, and we may assume that the air is constant specific heat or variable specific heat. So in these problems, because we're talking about open systems, we're interested in finding the specific enthalpy, H, and not the specific internal energy, U. But we're still using ideal gases, so we can use the ideal gas law. We can use it at a single state to try to fix maybe a temperature, or we can use it from state to state knowing that PV over T is constant. Remember that when we're talking about processes that deal with air as the working fluid, it's really important to be able to identify the isentropic processes in the system. Now, we'll use slightly different equations for the isentropic processes in Brayton cycles because we're trying to find delta H. But still, we have two choices here. Are we talking about variable specific heat, where we'll look things up on table A22, or we're talking about constant specific heat, where we'll simplify delta H to be equal to the specific heat times the change in temperature. If we're looking things up on table A22, we'll be looking for pressure ratios, often called compressor pressure ratios, which is not easy to say. And we'll look at the ratio of the pressures being equal to the ratio of the reduced pressures when we look on table A22. But if we're using constant specific heat, we'll again look for an equation that has K in the exponent, but this time it doesn't make sense to talk about volume ratios for open systems, like we did with internal combustion engines. We'll be talking about pressure ratios. It's always important to remember that we can only use these expressions when we're talking about isentropic processes where S stays constant. So here's a brief example that we'll go over for an ideal 4-component Brayton cycle. We're given a state table, so we see that the compressor pressure ratio is 8, and we know the inlet temperatures, or the temperatures at state 1 and state 3, and we're asked to find the net work over the mass flow rate, and we're asked to find the thermal efficiency. So first I want to find a symbolic solution. So I'll look at every different component in my system and I'll do a first law analysis. I'll make different assumptions for the turbine and the compressor than for the heat exchangers because I know that the turbines and compressors are adiabatic so that they're generating power. For those components, we know that we're going to get that W dot over M dot is delta H. And this time, the delta H for these components is H in minus H out. I'll add these things together and let the first law take care of the sign of each of these terms. I've color-coded things here so that positive terms related to the turbine are green and negative terms related to the compressor are red. If I'm doing a cold air standard analysis, I change these delta H's to Cp times delta T. So I can pull a Cp out from this whole equation and all my H's become T's. Now I don't know T4, I do know Cp, I don't know T2, I do know T3, and I do know T1. So if I could fix all my states, I would know the net work per mass flowing through the system. And that's good because it's the numerator in my thermal efficiency. But now I also need to do a first law analysis on the combustor, which is passive, meaning that there is no power consumed or generated in my combustor. And then I can see that its equation is going to be H out minus H in if I look for the heat added per unit mass flowing through the system. So now I have an equation. If I was doing variable specific heat, I would leave these all as H's. But since I'm doing a constant specific heat problem, I pull Cp out of both the numerator and the denominator, so my H's become T's. And then because both the numerator and the denominator are multiplied by Cp, I can cancel it out and I have an equation that's just left with the temperatures. Like I said before, I don't know T4 or T2. I do know T3 and T1. So now all that's left to do is fix all the states. So if I was doing this on an exam, I would try to run through the symbolic solutions first because that demonstrates that I understand how to do the problem. And now I'm left with symbolic solutions for the work or the net work of the cycle per unit mass flowing through the system and the thermal efficiency. All I have to do is fix my states. So when we do cycles that work with ideal gases, it's really important to recognize which processes are isentropic. And in this case, as we move between 1 and 2, or we could think of this as 2s because it's an isentropic process, we know that this is isentropic. So now I can look for the right expression that has k in the exponent. And in this case, because I know the compressor pressure ratio, we're going to use this equation spotlighted on the slide. I know the compressor pressure ratio, P2 over P1, is equal to R, or 8 in this case. I can look up K for air, but I know that it's 1.4. And now I have an expression for T2, which in this case is 543 degrees Kelvin. And I can put that in my state table. As I move from state 2 to state 3, it's nice because I already know the temperature at state 3, but I need to know the pressure here to complete my state table. But here, the pressure is constant as we move through the combustor, which is the process that's happening between state 2 and state 3. So my pressure stays at 800. Now I have to go between state 3 and state 4. The trick here is we have to remember that the pressure ratio is the same through the turbine as it is through the compressor. Or in this case, we're pulling air from the atmosphere, but we're also putting air back into the atmosphere. So the pressure at the exit of a jet or a nozzle is equal to the atmospheric pressure. So my pressure at 4 is 100 kilopascals. Again, I'm looking for an isentropic process relationship for a cold air standard problem, so I look for an expression that has K in the exponent, and in this case I know the pressure ratio. Typically for open systems we're going to use this equation, and for closed systems where we know volume ratios, like internal combustion engines, we use the volume ratio. So now I know that this equation I can use. Looks like when I went from 1 to 2, but now we have 1 over R instead of R that we're taking to the power of K minus 1 over K. I put some numbers into my calculator and I find the temperature at state 4. So because I already have symbolic solutions for the things that I'm looking for, I can just plug my numbers from my state table into my symbolic solutions, and I find that the net work per kilogram flowing through the system is 520.7 kilojoules per kilogram. And I see that my efficiency is 44.8, or almost 45%. You can see that this is a much larger efficiency than we typically got in the Rankine cycle problems that we did. And we haven't even done anything to improve the efficiency in our Brayton cycle yet. So you might ask yourself, how can we improve efficiency in Brayton cycles? Well, for that, you'll have to tune in next time to virtual thermodynamics. Thank you, and I'll see you all again next time.